was the next part here? It was this non-conducting sample. So we want to load the paper. All right, you can load. Yeah. Machine is on 15 kilovolt. We have beam intensity 3. So, and see how it evolves, so to say. The first thing we can do is we can just try to turn on the beam, and since it's we have a non-conducting sample there, and we can see how does it look like. You know, what happens if you actually have a series of non-conducting samples and we try to monitor this.
Interesting.
Wow. We can try to wanted to see where the edge of the paper is. I try to move to that position. So we had silver paint around the edges. So is this that area perhaps that you are seeing? Yeah, I think this is the silver paint. All right, we do the approach according to the protocol.
Okay.
All right, are you satisfied?
I think so.
Mm-hmm.
What happened?
Yeah, I moved it up to 10 millimeter.
Okay.
Left and right.
Okay. Oh, that was much better.
Yeah. Yeah, and then we pull in the detector, the backscatter detector. We have 10 millimeter, so it should be safe. Mm-hmm. And if we zoom out now, you can see that there is a very tiny hole there now.
Mm-hmm.
So you remember in yesterday's training session when we pull in the backscatter detector, then the maximum view field went from 3 millimeter to 600 micron.
Yeah.
But since we're going to use the low vacuum mode, we need to have this extra aperture in the pole piece.
Yeah.
That's basically a miniature hole. Mm. And the size of this hole, you see, it's about 200 micron.
I see.
So if we thought the backscatter limited us to 600 micron, now we're down to 200 micron.
Right.
In our maximum view field, so to say. But we shall pull it up to correct working distance also. So. All right. Looks like there is stigmatism, right?
Yeah.
You want to correct that?
Sure.
You remember how to do? You need to find the midpoint first.
Oh, that's right. Yeah. I'm not sure.
Yeah, I mean, you see, right? Mm. There you have the lines, right?
Yeah.
It starts to come there.
Mm.
And then it switches over, right? Here, now the lines start to come a little bit in that direction.
Somewhere around there.
So sometimes it I tend to, after you've done this for a long time, you stop looking for these lines and you just look on the shape and want to see that it becomes symmetric in the features. That you get that experience if you run this for some time. So. But all right, try some stigmatism now on the ball there and see if you can make the image sharp. You can increase this also so you have a little bit more power there. A little bit up and down also. Something like that. So, since this is a paper material we're going to study, I mean, paper fibers are micrometer, I mean, in diameter, and then they are like 10 hundredths long. So let's zoom out now to our, what shall I say, maximum view field. I mean, here we can see it's about 100 microns actually, not 200. If you want to sort of keep the whole square view, right? The aperture is 200, so if you want to have not a round circle to look on, but a square, then okay, we are limited to 100. Take the joystick here now and run out to the paper here. So now we're coming out on the paper here. So this is how it looks like when we have severe charging. You see these stripes go straight across. And we also see that things becoming more bright and some parts become more black and things like that. So that is typical charging phenomenon. And if we try to scan here now, let's say we want to try to take a picture here now, a standard 1500 by 1500 picture pixels, and let's take a 32 second scan time. Let's see how that will look like. So we will create the world's most ugliest image here now. And you see it sort of blow out. It's very hard to see anything. And now the paper fibers is, like a network and so on. It's if we would have like a more smooth material that is non-conducting, like a plastic or something like that, then it will charge up more evenly. And in that case, we will start to see features in that film. And if we study long enough, we will actually start to see an image. And the image will be a picture of the roof of the chamber. Because the electrons, it's so charged up the surface that the electrons sort of bounce back up and hit the roof of the chamber and then goes to the detector. So we are scanning in the roof due to this. It becomes like an electron mirror, the whole thing. But as I said, the paper is a little bit rough to actually show that. You can go even further out. You see, all the dots we see here is the silver paint. So we are still halfway into the paint. So if we really go out, and now we are closer to the center. You can try to click on the absolute center here. Here, you see, right? If you try to scan this. And it's very important to understand that when we're scanning here, it looks like we can see something. But the image is so distorted and deflected, so it's hard to actually interpret what we are looking on. So, and sometimes you can fool yourself from charging phenomena, that it actually looks like there is a feature, but then the feature actually doesn't exist. It's just ghosts by charging, so to say. So now let's switch to low vacuum mode, and we can. This is the SC detector. We also have the BEC detector. How does that work? So this is the BSE image. The backscatter electrons is of course of higher energy, so they are less affected by the charging. But we see, I mean, even these high energy electrons can't survive a non-coated surface. I mean, and especially if we compare these two images, can I make that smaller? If we compare the SE image, oh, this was the, so we see that they do resemble each other a little bit, but it's like very hard to say something about it. So let's try the low vacuum mode now. And we can only run the low vacuum mode if we have the aperture inserted. So it's very important that we make sure that we have that put in. And then you can run between 0 and 500 Pascal. And 500 Pascal is a lot actually. So, but usually you want to be within 30 to 70 in that range. That's the sweet spot. So let's try that. So it says here, is the aperture inserted? If you're not, we have that. So we try that. So now we can see that we have a complete different pressure. We will be at 50 Pascal in the chamber. We can see here chamber pressure, 5 to the power of 10 to 1. That's 50 Pascal, around that. So let's try. All right, so if we scan, and now it is the backscatter detector still using. So then we can compare. This one is always in front. It's a little bit annoying. So if we compare the images, I mean, in the low vacuum mode, we can actually see something.
Yeah.
So the pressure inside there removes the charging from the surface. And we can see that, I mean, resolution-wise, it's a little bit, what shall I say, blurred. So this is the punishment. The higher pressure, the more worse the resolution becomes. So if we drop this, we can go to 20 Pascal here. It's on 38 now. We can watch the scan there, see how it evolves. So what we're going to see here is that, I mean, the lower and lower in pressure we go, the better the image quality will be, but the charging will also start to come back.
Yeah.
We can just write 2 here perhaps and see when it goes downwards. It's on 29 now, 27. You see it starts to glow, right, in the image.
Yeah.
So now we are on 20. So now the pressure starts to become too much towards vacuum, you can say.
Yeah.
And now the charging starts to emerge. So, I mean, still, and now we are on 15 Pascal. And 15 Pascal is still much higher than the regular vacuum we have in the chamber. So we're still in the low vacuum mode, so to say. But you can see that it's 12 Pascal right now. And that's too little to suppress the charging.
Yeah.
So that's what I'm saying. I mean, you are in like 30 to 70 range. So if I go up here to 100, now it's 95 here. Let's let it stabilize a little bit. Now it's 100. now we see all charging is gone, and it was gone when we ran it to 50 also. But now it's even more blurred because it's too much gas inside. And all this is the backscatter detector. We can only run backscatter detector due to the gas. The secondary electrons will not reach the secondary electron detector. They're too slow. And you can see here we cannot even choose the secondary electron detector. So this is a little bit limited in that way. But this is one way of monitoring something that you don't want to coat. So it is possible. We take out the aperture first. So let's do that. And then we need to open the door. So then I can film. So we click here on vent. All right, so now we have vented the whole chamber. We just pull everything out. So here it comes, so you can see the carousel now on the stage that we loaded through the airlock. And what we want to do now is the aperture is on the bottom part there. But now you see the detector, the backscatter detector is in the way.
Yeah.
So I retract that. So here is the aperture now, sitting as a plug there. And we want to grab that one. Like that. So here you can see how it looks like.
I see. Okay.
Small little plug. And these ones we keep them inside the vacuum here, so we just leave it there.
Okay.
And when you push it in, it's a little bit of a rubber gasket around the aperture. So when you put it in, you feel it, and then you push it so it becomes completely flat.
I see.
And that's it. So now everything is removed. So when we close the chamber doors, there is some things to be careful about. The first is the gasket here. You can see the gasket tends to slip out. So you need to make sure the gasket follows all the way through. And then you see also the cable to the stage. This you don't want to clamp it, right?
No.
So we need to make sure the gasket goes inside there. And then of course, if you're going to mount sample from this position, then you also need to make sure if you have big things that you don't crash it when it's closed the door.
Yes.
I mean, one can look on the camera view on the SEM software, right? But I mean now, since it already fitted when we took it out, this should not be any issue.
No.
Just close the door like that, and then a quick pump.